A crane is a type of machine, generally equipped with a hoist rope, wire ropes, chains, and sheaves, that can be used both to lift and lower materials and to move them horizontally. It is mainly used for lifting heavy things and transporting them to other places. It uses one or more simple machines to create mechanical advantage and thus move loads beyond the normal capability of a human. Cranes are commonly employed in the transport industry for the loading and unloading of freight, in the construction industry for the movement of materials, and in the manufacturing industry for the assembling of heavy equipment. The first known construction cranes were invented by the ancient Greeks and were powered by men or beasts of burden, such as donkeys. These cranes were used for the construction of tall buildings. Larger cranes were later developed, employing the use of human treadwheels, permitting the lifting of heavier weights. In the High Middle Ages, harbour cranes were introduced to load and unload ships and assist with the construction. Some were built into stone towers for extra strength and stability. The earliest cranes were constructed from wood, but cast iron, and steel took over with the coming of the Industrial Revolution. For many centuries, power was supplied by the physical exertion of men or animals, although hoists in watermills and windmills could be driven by the harnessed natural power. The first mechanical power was provided by steam engines, the earliest steam crane being introduced in the 18th and 19th century, with many remaining in use well into the late 20th century. Modern cranes usually use internal combustion engines or electric motors and hydraulic systems to provide a much greater lifting capability than was previously possible. Although manual cranes are still utilized where the provision of power would be uneconomic, cranes exist in an enormous variety of forms, each tailored to a specific use. Sizes range from the smallest jib cranes, used inside workshops, to the tallest tower cranes, used for constructing high buildings. Mini cranes are also used for constructing high buildings, in order to facilitate constructions by reaching tight spaces. Finally, we can find larger floating cranes, generally used to build oil rigs and salvage sunken ships. Some lifting machines do not strictly fit the above definition of a crane, but are generally known as cranes, such as stacker cranes and loader cranes. History. Ancient Greece. The crane for lifting heavy loads was invented by the ancient Greeks in the late 6th century BC. The archaeological record shows that no later than c. 515 BC distinctive cuttings for both lifting tongs and Lewis irons begin to appear on stone blocks of Greek temples. Since these holes point at the use of a lifting device, and since they are to be found either above the center of gravity of the block, or in pairs equidistant from a point over the center of gravity, they are regarded by archaeologists as the positive evidence required for the existence of the crane. The introduction of the winch and pulley hoists soon lead to a widespread replacement of ramps as the main means of vertical motion. For the next 200 years, Greek building sites witnessed a sharp reduction in the weights handled. The new lifting technique made the use of several smaller stones more practical than fewer larger ones, in contrast to the archaic period with its tendency to ever-increasing block sizes. Greek temples of the classical age, like the Parthenon, invariably featured stone blocks weighing less than 15 to 20 metric tons. Also, the practice of erecting large monolithic columns was practically abandoned in favor of using several column drums. Although the exact circumstances of the shift from the ram to the crane technology remain unclear, It has been argued that the volatile social and political conditions of Greece were more suitable to the employment of small, professional construction teams than of large bodies of unskilled labor, making the crane more preferable to the Greek polis than the more labor-intensive ramp which had been the norm in the autocratic societies of Egypt or Assyria. The first unequivocal literary evidence for the existence of the compound pulley system appears in the mechanical problems attributed to Aristotle, but perhaps composed at a slightly later date. Around the same time, block sizes at Greek temples began to match their archaic predecessors again, indicating that the more sophisticated compound pulley must have found its way to Greek construction sites by then. Ancient Rome. The heyday of the crane in ancient times came during the Roman Empire, when construction activity soared and buildings reached enormous dimensions. The Romans adopted the Greek crane and developed it further. We are relatively well informed about the lifting techniques, thanks to rather lengthy accounts by the engineers Vitruvius and Heron of Alexandria. There are also two surviving reliefs of Roman treadwheel cranes, with the Hator tombstone from the late 1st century AD being particularly detailed. The simplest Roman crane, the tris pastus, consisted of a single beam jib, a winch, a rope, and a block containing 3 pulleys, having thus a mechanical advantage of 3 to 1. It has been calculated that a single man working the winch could raise 150 kilograms, assuming that 50 kilograms represent the maximum effort a man can exert over a longer time period. Heavier crane types featured 5 pulleys or, in case of the largest one, a set of 3 by 5 pulleys and came with 2, 3 or 4 masts, depending on the maximum load. The polyspace, when worked by 4 men at both sides of the winch, could readily lift 3,000 kilograms. If the winch was replaced by a treadwheel, the maximum load could be doubled to 6,000 kilograms at only half the crew. Since the treadwheel possesses a much bigger mechanical advantage due to its larger diameter, this meant that, in comparison to the construction of the Egyptian pyramids, where about 50 men were needed to move a 2.5-ton stone block up the ramp, the lifting capability of the Roman polyspace proved to be 60 times higher. However, numerous extant Roman buildings which feature much heavier stone blocks than those handled by the polyspace indicate that the overall lifting capability of the Romans went far beyond that of any single crane. At the Temple of Jupiter at Baalbek, for instance, the architrave blocks weigh up to 60 tons each, and one cornice block even over 100 tons, all of them raised to a height of about 19 meters. In Rome, the capital block of Trajan's column weighs 53.3 tons, which had to be lifted to a height of about 34 meters. It is assumed that Roman engineers lifted these extraordinary weights by 2 measures. First, as suggested by Heron, a lifting tower was set up, whose 4 masts were arranged in the shape of a quadrangle with parallel sides, not unlike a siege tower, but with the column in the middle of the structure. Second, a multitude of capstans were placed on the ground around the tower, for, although having a lower leverage ratio than treadwheels, capstans could be set up in higher numbers and run by more men. This use of multiple capstans is also described by Ammianus Marcellinus in connection with the lifting of the Lateranense obelisk in the Circus Maximus. The maximum lifting capability of a single capstan can be established by the number of Lewis iron holes bored into the monolith. In case of the Baalbek architrave blocks, which weigh between 55 and 60 tons, 8 extant holes suggest an allowance of 7.5 ton per Lewis iron, that is, per capstan. Lifting such heavy weights in a concerted action required a great amount of coordination between the work groups supplying the force to the capstans. Middle Ages. During the High Middle Ages, the treadwheel crane was reintroduced on a large scale after the technology had fallen into disuse in Western Europe with the demise of the Western Roman Empire. The earliest reference to a tread wheel reappears in archival literature in France about 1225, followed by an illuminated depiction in a manuscript of probably also French origin dating to 1240. In navigation, the earliest uses of harbour cranes are documented for Utrecht in 1244, Antwerp in 1263, Bruges in 1288 and Hamburg in 1291, while in England the tread wheel is not recorded before 1331. Generally, vertical transport could be done more safely and inexpensively by cranes than by customary methods. Typical areas of application were harbours, mines, and, in particular, building sites where the tread wheel crane played a pivotal role in the construction of the lofty Gothic cathedrals. Nevertheless, both archival and pictorial sources of the time suggest that newly introduced machines like tread wheels or wheelbarrows did not completely replace more labor-intensive methods like ladders, hods and hand barrows. Rather, old and new machinery continued to coexist on medieval construction sites and harbors. Apart from tread wheels, medieval depictions also show cranes to be powered manually by windlasses with radiating spokes, cranks, and by the 15th century also by windlasses shaped like a ship's wheel, to smooth out irregularities of impulse and get over dead spots in the lifting process. Flywheels are known to be in use as early as 1123. The exact process by which the tread wheel crane was reintroduced is not recorded, although its return to construction sites has undoubtedly to be viewed in close connection with the simultaneous rise of Gothic architecture. The reappearance of the tread wheel crane may have resulted from a technological development of the windlass from which the tread wheel structurally and mechanically evolved. Alternatively, the medieval tread wheel may represent a deliberate reinvention of its Roman counterpart drawn from Vitruvius's architecture, which was available in many monastic libraries. Its reintroduction may have been inspired, as well, by the observation of the labor-saving qualities of the water wheel with which early tread wheels shared many structural similarities. Structure and placement. The medieval tread wheel was a large wooden wheel turning around a central shaft with a treadway wide enough for two workers walking side by side, while the earlier compass arm wheel had spokes directly driven into the central shaft. The more advanced clasp arm type featured arms arranged as cords to the wheel rim, giving the possibility of using a thinner shaft and providing thus a greater mechanical advantage. Contrary to a popularly held belief, cranes on medieval building sites were neither placed on the extremely lightweight scaffolding used at the time nor on the thin walls of the Gothic churches, which were incapable of supporting the weight of both hoisting machine and load. Rather, cranes were placed in the initial stages of construction on the ground, often within the building. When a new floor was completed, and massive tie beams of the roof connected the walls, the crane was dismantled and reassembled on the roof beams from where it was moved from bay to bay during construction of the vaults. Thus, the crane grew and wandered with the building, with the result that today all extant construction cranes in England are found in church towers, above the vaulting and below the roof, where they remained after building construction for bringing material for repairs aloft. Less frequently, medieval illuminations also show cranes mounted on the outside of walls with the stand of the machine secured to putlogs. Mechanics and operation. In contrast to modern cranes, medieval cranes and hoists, much like the counterparts in Greece and Rome, were primarily capable of a vertical lift, and not used to move loads for a considerable distance horizontally as well. Accordingly, lifting work was organized at the workplace in a different way than today. In building construction, for example, it is assumed that the crane lifted the stone blocks either from the bottom directly into place, or from a place opposite the center of the wall from where it could deliver the blocks for two teams working at each end of the wall. Additionally, the crane master, who usually gave orders at the treadwheel workers from outside the crane, was able to manipulate the movement laterally by a small rope attached to the load. Slewing cranes, which allowed a rotation of the load and were thus particularly suited for dockside work, appeared as early as 1340. While ashlar blocks were directly lifted by sling, Louis devils clamped. Other objects were placed before in containers like pallets, baskets, wooden boxes or barrels. It is noteworthy that medieval cranes rarely featured ratchets or brakes to forestall the load from running backward. This curious absence is explained by the high friction force exercised by medieval treadwheels, which normally prevented the wheel from accelerating beyond control. Harbour usage. According to the present state of knowledge, unknown in antiquity, stationary harbour cranes are considered a new development of the Middle Ages. The typical harbour crane was a pivoting structure equipped with double treadwheels. These cranes were placed docksides for the loading and unloading of cargo, where they replaced or complemented older lifting methods like seesaws, winches in yards. Two different types of harbour cranes can be identified with a varying geographical distribution. While gantry cranes, which pivoted on a central vertical axle, were commonly found at the Flemish and Dutch coastside, German sea and inland harbours typically featured tower cranes, where the windlass and treadwheels were situated in a solid tower with only jib arm and roof rotating. Interestingly, dockside cranes were not adopted in the Mediterranean region and the highly developed Italian ports, where authorities continued to rely on the more labor-intensive method of unloading goods by ramps beyond the Middle Ages. Unlike construction cranes, where the work speed was determined by the relatively slow progress of the masons, harbour cranes usually featured double treadwheels to speed up loading. The two treadwheels, whose diameter is estimated to be 4 meters or larger, were attached to each side of the axle and rotated together. The capacity was 2 to 3 tons, which apparently corresponded to the customary size of marine cargo. Today, according to one survey, 15 treadwheel harbour cranes from pre-industrial times are still extant throughout Europe. Some harbour cranes were specialized at mounting masts to newly built sailing ships, such as in Gdansk, Cologne and Bremen. Beside these stationary cranes, floating cranes, which could be flexibly deployed in the whole port basin, came into use by the 14th century. Early modern-age airlifting tower, similar to that of the ancient Romans, was used to great effect by the Renaissance architect Domenico Fontana in 1586 to relocate the 361 heavy Vatican obelisk in Rome. From his report, it becomes obvious that the coordination of the lift between the various pulling teams required a considerable amount of concentration and discipline, since, if the force was not applied evenly, the excessive stress on the ropes would make them rupture. Cranes were also used domestically during this period. The chimney or fireplace crane was used to swing pots and kettles over the fire, and the height was adjusted by a trammel. Industrial Revolution. With the onset of the Industrial Revolution, the first modern cranes were installed at harbours for loading cargo. In 1838, the industrialist and businessman William Armstrong designed a hydraulic water-powered crane. His design used a ram in a closed cylinder that was forced down by a pressurized fluid fluid entering the cylinder. A valve regulated the amount of fluid intake relative to the load on the crane. In 1845 a scheme was set in motion to provide piped water from distant reservoirs to the households of Newcastle. Armstrong was involved in this scheme, and he proposed to Newcastle Corporation that the excess water pressure in the lower part of town could be used to power one of his hydraulic cranes for the loading of coal onto barges at the quayside. He claimed that his invention would do the job faster and more cheaply than conventional cranes. The corporation agreed to his suggestion, and the experiment proved so successful that 3 more hydraulic cranes were installed on the quayside. The success of his hydraulic crane led Armstrong to establish the Elswick Works at Newcastle, to produce his hydraulic machinery for cranes and bridges in 1847. His company soon received orders for hydraulic cranes from Edinburgh and Northern Railways and from Liverpool docks, as well as for hydraulic machinery for dock gates in Grimsby. The company expanded from a workforce of 300 and an annual production of 45 cranes in 1850, to almost 4,000 workers producing over 100 cranes per year by the early 1860s. Armstrong spent the next few decades constantly improving his crane design. His most significant innovation was the hydraulic accumulator, where water pressure was not available on site for the use of hydraulic cranes. Armstrong often built high water towers to provide a supply of water at pressure. However, when supplying cranes for use at New Holland on the Humber estuary, he was unable to do this because the foundations consisted of sand. He eventually produced the hydraulic accumulator, a cast-iron cylinder fitted with a plunger supporting a very heavy weight. The plunger would slowly be raised, drawing in water, until the downward force of the weight was sufficient to force the water below it into pipes at great pressure. This invention allowed much larger quantities of water to be forced through pipes at a constant pressure, thus increasing the crane's load capacity considerably. One of his cranes, commissioned by the Italian Navy in 1883 and in use until the mid-1950s, is still standing in Venice, where it is now in a state of disrepair. Mechanical principles. There are 3 major considerations in the design of cranes. First, the crane must be able to lift the weight of the load. Second, the crane must not topple. Third, the crane must not rupture. Stability. For stability, the sum of all moments about the base of the crane must be close to 0 so that the crane does not overturn. In practice, the magnitude of load that is permitted to be lifted is some value less than the load that will cause the crane to tip, thus providing a safety margin. Under U.S. standards for mobile cranes, the stability limited rated load for a crawler crane is 75% of the tipping load. The stability limited rated load for immobile cranes supported on outriggers is 85% of the tipping load. These requirements, along with additional safety-related aspects of crane design, are established by the American Society of Mechanical Engineers in the volume ASME B 30.5-2014 Mobile and Locomotive Cranes. Standards for cranes mounted on ships or offshore platforms are somewhat stricter because of the dynamic load on the crane due to vessel motion. Additionally, the stability of the vessel or platform must be considered. For stationary pedestal-looking post-mounted cranes, the moment created by the boom, jib, and node is resisted by the pedestal base-looking post. Stress within the base must be less than the yield stress of the material, or the crane will fail.